We need to determine the frequency response of this circuit. The input is this voltage source U of t, and our output is the voltage across this capacitor Y of t. Since it's a frequency response, what we're looking for is a steady state sinusoidal analysis, and we want h of j omega, which is the ratio of the output voltage phasor as a function of frequency to the input voltage phasor also as a function of frequency. So let's convert this circuit to the frequency domain to start out with. So our 7 ohm resistor's impedance is 7 ohms. This voltage source becomes a phasor U as a function of omega. 4 ohm resistor has 4 ohms of impedance. The capacitor has an impedance of 1 over j omega c, which is going to be 2 over j omega. And the voltage phasor Y of j omega is our output across the capacitor. And finally, this 2 ohm resistor. So this voltage source means that we know the voltage across these two terminals. If we combine these elements here, then that will give us a voltage divider. So these are in parallel, so the equivalent impedance here, ZEQ, is 2 ohms times 2 over j omega over 2 ohms plus 2 over j omega. If I multiply top and bottom by j omega, this becomes 4 over j2 omega plus 2. So now, using a voltage divider, Y of j omega is the total voltage, U of j omega, times this impedance, 4 over j2 omega plus 2, over the sum of this 4 ohm resistance and this impedance. So we have 4 plus 4 over j2 omega plus 2. And we're really done at this stage, but I think I'll clear this j2 omega plus 2 out of the denominator, so I'll multiply top and bottom by j2 omega plus 2, and then dividing out u of j omega, so h of j omega is y of j omega over u of j omega. And if I do this multiplication, this becomes 4 over 4 times j2 omega plus 2 plus 4, which, if I simplify it down, becomes 4 over j8 omega plus 12. When I do a frequency response, there's no reason not to check this result at low and high frequencies. Getting rid of some of the stuff that I don't need anymore. I can take advantage of what I know about the capacitor's behavior at low and high frequencies. So as omega goes to 0, the capacitor looks like an open circuit. I have this 7 ohm resistor here, not that it matters because it's in parallel with a voltage source. This is U of J0, 0 radians per second. 4 ohms, an open circuit, 2 ohms, and this voltage is Y of J0. So this is a voltage divider now. Y of J0 is equal to U of J0 times 2 ohms over 2 ohms plus 4 ohms. So H of J0 is equal to 1/3. If I plug 0 in here, H of J0 is equal to 4 over 0 plus 12, which is also 1/3. It looks like we're in pretty good shape. I also want to take a look as omega goes to infinity. So that resistance, this voltage source, U of J infinity, 4 ohms. The capacitor becomes a short circuit at high frequencies, 2 ohms. And there is, by definition, no voltage difference across a short circuit. So Y of J infinity is equal to 0. So H of J infinity is equal to 0. And if I plug infinity in here, H of J infinity is equal to 4 over infinity plus 12, which is just 0, which checks out. Looks like we're in good shape and we have a usable frequency response. Now let's sketch the magnitude response of the circuit. So what we want is a plot as a function of frequency, so omega, which is always in radians per second, and the magnitude of H of J omega. And in general, in our sketches, we'll want to label the low frequency gain, the high frequency gain, and label the cutoff frequency and its value. We can determine all that from the frequency response, but I'm going to treat this as if it's an entirely separate problem from part A, because I can determine all this stuff directly from the circuit. When omega is equal to 0, we have the same thing we had before when we checked our values. 7 ohms, U of J0, 4 ohms. At low frequencies, the capacitor looks like an open circuit, and 2 ohms. And as before, we said that's a voltage divider between this 2 ohm resistance and this 4 ohm resistance. So Y of J0 is equal to 1/3 U of J0. And at low frequencies, H of J0 is 1/3. As omega goes to infinity, another problem that we already did, the capacitor looks like a short circuit at high frequencies. And of course, there is no voltage difference across a short circuit, so Y at J infinity is equal to 0, which means that this goes to 0 at high frequencies. Now we just need to find the cutoff frequency. Probably the easiest way to do that is to notice that for a first order circuit, the cutoff frequency is 1 over the time constant, and for an RC circuit, the time constant is the equivalent resistance seen by the capacitor times the capacitance. So let's find the equivalent resistance. We have a 7 ohm resistor, we short the voltage source, a 4 ohm resistor, these are the terminals that we're finding the equivalent resistance across, and a 2 ohm resistor. So this 7 ohm resistance is in parallel with a short circuit, which makes this entire side a short circuit. So Req is 4 ohms in parallel with 2 ohms, which is 4 times 2 over 4 plus 2, or 8 over 6. So tau is equal to 8 over 6 ohms times a half a farad, or 8 over 12 seconds. That means that the cutoff frequency, omega sub c, is 1 over tau, so that's 12 over 8 radians per second. The cutoff frequency is 12 over 8